Okay, should I start? Good. So, remember what we just did is found out this is the binomial distribution for the more general case than the one we did last class, which we were only considering P equals to Q equals to 1/2. So all these became the factor 1 over 2 to the n. You see, because you have 1/2 to the n plus times 1/2 to the n minus n plus is 1/2 to the n. So this is the distribution we obtained. This is the binomial, only that in a biased case, when the two states don't have the exact same probability. Still binary. So what I want to show you, this is the binomial. I want to obtain the Gaussian approximation to this. But I want to show you in a different way, that if I just take blindly this and I expand to second order, the way we learned in Calc 1 in Taylor expansion, you just get exactly the expression we were doing before. Only that you'll have to be a little bit careful, because in order to expand you need to take derivatives and you have factorials. You know, a derivative of factorial, we have to think a little bit what is the derivative of factorial. And besides that, this is the expression we have. And it turns out that it's a little simpler if instead of expanding this to second order, I expand the logarithm. It will be the same, because the maximum of the function and the maximum of the logarithm will fall at exactly the same place, because logarithm is an increasing function. So I can do the expansion in this quantity, and at the end of the calculation, and I exponentiate again. That's a trick you always do, because then the factors become sums, and it's easier, you know, to deal with them. So, what will be the expansion of these things? Well, like any expansion, will be the logarithm of the function calculated at the maximum. Okay? That's the first step. You calculate the function at the maximum, plus the derivative of the function with respect to n plus, calculated at the maximum, times n plus minus n plus maximum. Okay? And the next term is 1/2 times the second derivative of the logarithm of Pn of n plus with respect to n plus twice, calculated at n plus maximum, times n plus minus n plus maximum squared. Of course, I need to calculate who all these things are. Who is n plus maximum, and what is this derivative, and what is this derivative. So I need to calculate 3 things. Actually, only 2 things. Because once I find the maximum, the derivative calculated at the maximum will be 0. So this term, in any expansion, when you expand the function around the maximum, the first term does not appear. Okay? When you expand anywhere else, yes. But if you expand around the maximum, by definition, the derivative is 0. So what I have is, in reality, the logarithm of Pn calculated at n plus maximum plus 1/2 the second derivative, let me call it a2 for the time being, but it's some number because I am calculating it exactly at the maximum. It's some number times n plus minus n plus maximum squared. All I did is I said the first term will vanish, but the second term I'm giving it a name, but we'll have to calculate it. So if this is the case, then Pn, this is the logarithm of Pn plus, okay? Expanded to second order. So P of n plus will be what? The exponential of this is P evaluated at n plus maximum times e to the 1/2 a2 n plus minus n plus maximum squared. So any expansion of a function around the maximum, if you do it in second order, will have to take this shape. Okay? The value of the function times this, where I remember you, n plus maximum, I have still to determine where is the maximum of the function Pn of n plus, and I have to calculate this quantity, the second derivative of the logarithm at precisely the maximum. So I need first to calculate the maximum, then take the second derivative of the logarithm in that place where I just calculated, and then that's the expansion. So you see, it seems like there are only two things to be calculated. And so let me calculate the first one. Where is the maximum? So let me write it. The expansion is logarithm Pn of n plus. No, let me write it. Pn of, I don't need that. I am trying to get the derivative. So let me take the logarithm. So by definition, this is logarithm of n factorial minus the logarithm of n plus factorial minus the logarithm of n minus n plus factorial plus n plus ln p plus n minus n plus ln q. Okay? All I did is I took my original expression that you remember was Pn of n plus was the factorial of this divided the factorial of this and the factorial of this times p to the n plus times q to the n minus n plus. I took logarithms in each term. So you get it like this, and you see why this is nice, because then you take the derivative term by term. Since I need to calculate the maximum, what I have to do is to take the derivative of this, equate to 0, and find out for which value of n plus the derivative of this expression is 0. So you see that I have here the problem that I mentioned. I need to derive this. N is a constant, so I don't care when I take the derivative is 0, but I have the logarithm of n plus, and I am deriving with respect to n plus. So I need to learn that, so this will be like a little aside calculation. What is, say, the derivative of the logarithm of n factorial with respect to n, where n is any number. In my case, it would be n plus. But let me try to calculate that. Well, we have two ways of showing it, what it is. One is saying, well, I will use the fact that this is a discrete quantity. So this is, let me do the derivative, is I need to do logarithm of n plus n, or when I'm doing for n plus 1 factorial minus logarithm of n factorial divided n plus 1 minus n. Okay. So I am using a sort of discrete version of the logarithm. This is an auxiliary calculation, you understand? So I am just trying to find out how to calculate this derivative. So if I believe that I can treat the logarithm as something that jumps in steps of 1, that's what I'm doing. And now this is easy, because this is the logarithm of n plus 1 factorial over n factorial, which is simply n plus 1 divided 1. So the derivative of logarithm of n factorial with respect to n is just the logarithm of n plus 1, or approximately the logarithm of n. Well, so when you need to derive logarithm of n factorial, you get the logarithm of n. That is one way. If you don't like that too much, you can do another thing that will give you the same result. Replace that by the Stirling formula. So So I need to derive with respect to n what? The logarithm of n factorial, which is, we learned this, n plus 1/2 ln n minus n minus square root of 2 pi, right? Minus ln of 2 pi. Okay, we learned that this is the Stirling approximation to logarithm of n factorial. So take the derivative here. What do you get? I derive here, I get ln n. When I leave this, when I derive here, when I leave this and I derive here, I get 1 over n. So n plus 1/2 over 1. N plus 1/2 over n gives me 1 plus 1 over 2n. When I take the derivative here, I get minus 1, and the derivative here is 0 because that's a constant. So the 1 and 1 cancel, and what do you get? Ln n. Again, ln n plus a very small number. You understand that n is 10 to the 23, and so this is 1 over 10 to the 23, so I can forget. So, moral of the story, the derivative of ln n factorial is just ln n. And I need, because I have to come to this expression that I have right here and take derivatives. So let me show the expression again, and you will see that now calculating the derivatives is quite easy. The derivative of this is 0, this is a constant. Here I will get ln n factorial. Here I will get ln n minus n factorial with a plus sign, because I have a minus. And here I will get ln p, and here I will get minus ln q. Okay? Because I'm deriving with respect to n plus. So let me write that result. So the whole derivative. I get what I just said with words. I get minus ln n factorial plus ln n minus n factorial plus ln p minus ln q. And that has to be equal to 0. Remember, I'm trying to calculate the maximum, so I have to take, I took the derivative of my expression and I equate it to 0. When is that 0? Well, let me put it all together. When the logarithm of n minus n plus multiply times p divided n plus q is equal to 0. I combine all the logarithms in one expression. And if all this has to be, the logarithm has to be equal to 0, means that all this has to be equal to 1. In other words, n minus n plus p has to be equal to n plus q. What does it mean? That np has to be equal to n plus p plus q, or n plus. So the maximum is when n plus is equal to np. Surprise, surprise, before we calculated that the average value was np. Now we see that the maximum of the distribution is exactly at the average value. The maximum of this expression is when n plus is exactly np. So that was the first result I needed, that's the maximum. So n plus maximum is np. And now I need, remember the other thing I need is I need the second derivative of the logarithm of Pn of n plus with respect to n plus twice, precisely at the value np. But now that's easy, because the first derivative I calculated. I have to derive once more, and now it's a very trivial derivative. Okay, let me calculate here. This is the first derivative, right? So I need one more derivative with respect to n plus. This is 0, this is 0. I got minus 1 over n plus 1 over n minus n plus with the minus sign, because I have this minus, is minus 1 over n plus. So let me write the derivative. The second derivative is quite simple. The second derivative has only two terms that are minus 1 over n plus minus 1 over n minus 1. Did I write it correctly? Yes. Or, and calculate it at the maximum when n plus is np. 1 over np minus 1 over np minus 1 over n minus np. Or I can write this minus 1 over n and 1 over p plus 1 over q. 1 minus p is q. Okay? Or even more, you can even write it simpler as minus 1 over n, sum these two fractions, what you get? pq, and on top you get q plus p, which is 1. So this is the second derivative, minus 1 over n pq. So now we have all the ingredients to bake the cake. Remember, what we needed to write is that Pn of n plus is what? Is the function at the maximum. It's Pn. It's P at n plus maximum times e to the minus e to the 1/2 this. Remember, it was the second derivative. E to the 1 over 2 npq minus 1 over 2 npq n minus n plus maximum squared. That's the distribution. Where n plus maximum is n times np. So if you want p of n plus maximum, e to the minus n minus np divided to npq, and this goes square. There you have it. Did I write it correct? N plus, sorry. It's the variable. So I am doing an expansion. P of n plus, p sub n of n plus is just this. It's a function that decays quadratically with n plus. All I have to do is to replace this constant in front, but this is a constant because it's the function p of n plus that I have calculated at exactly that value. And in reality, the best thing to calculate it instead of starting to plug is saying, well, integrate all the way from 0 to infinity, and this has to give me 1. So this constant is a constant of normalization, obviously, because I have this factor times something in front, and the whole integral has to be 1, right? So if I calculate Pn of n plus, and I integrate this all the way from 0 to infinity, well, n plus can go all the way to n, but remember, I have e to the minus n plus square, so eventually the little tail is not important. I integrate this, I have to get 1, and this is p of the n plus maximum, which is what I need to calculate, times the integral of e to the n minus n plus np n plus minus np squared over minus 2 npq. And this goes from 0 to infinity. I get this integral, whatever I get here, multiplied by this, has to give me 1. So this will be the inverse of this. Okay, as usual, that's how you calculate the normalization constant. And these integrals, that's why we learn to calculate Gaussian integrals, okay? instead of integrating in n plus, I will integrate in n plus minus np. So the integral, this will be the integral from e to the minus, call it prime plus if you want, over 2np cubed. And now I go from minus np to infinity. And in the limit when n is very big, this is the same as integrating, since this decays. This is the same as going all the way from minus infinity to infinity, and this is a Gaussian integral. And not only that, but this integral we know how to calculate. Yeah, you have a question? Sorry.
Yeah, is it to the minus n prime plus squared?
Square, yeah.
On the lower in the solution.
No, I got 2npq because here was.
No, in the next part.
Here, oh, here, yes, absolutely right, sorry about that. So I change the variable, n plus minus np, I call it my variable of integration, which all it does is shoots the limit to minus infinity, so now I have a real Gaussian integral and I know how to calculate that. This is square root of pi over 1 over this, so it's the square root of 2 pi npq. Okay? So there you have it. This is this integral, so the constant of normalization has to be 1 over this. So now we finally got the Pn of n plus is 1 over square root of 2 pi npq e to the minus n plus minus np over 2x squared to npq. That's the whole expression. And if you are not convinced that this is the right result, so this is the actual distribution in a Gaussian way. If you are not convinced that this is right, just for the fun of it, replace for the case p equals 1/2, q equals 1/2, and you will see that you get a very old result. This is 1/4, so 2 over 4 is 2, so you get square root of 2 over pi n. Here you get e to the minus, again, this is 1/4, so you get e to the minus 2 n, because p and q are 1/2. And this is n plus minus n over 2. Okay? Which, if you remember correctly, n plus was n over 2 plus s. So this is s. Right? So you get e to the minus 2s squared over n. So you see, this is the expression when p was equal to q equals to 1/2. This is the most general case when p and q are any number. But you see, it's still the very similar quadratic decay as we learned. So you see, what I did is I generalized my previous result to the case p and q being arbitrary numbers, but I did it in a different way. I said, forget, I don't want to understand and think how many states. Let me take my expression, find where the maximum is, and expand around the maximum to second order. And that's what you get. So you see, a Gaussian approximation always is that. It's expanding some function around the maximum to second order and see how it decays out of the maximum. So this is something that I thought was a cute conclusion. Yes?
So basically when P and Q are distinct from each other, the decay is more...
yeah, of course. You know, this can have of course, this expression doesn't make sense if P is 1 and Q is 0, because they have a 0 here, so obviously then there is no distribution. But in general, this tells you something. If P and Q are not 1/2 and 1 is 0.9 and this becomes smaller, you will see it in examples of the Poisson immediately, but this is what happens, that simply the distribution becomes, this number here becomes smaller. Okay, so the distribution decays much faster because there is less variation. Remember that in the extreme case, there is no variation at all. So this number has to become much, much smaller. Okay, let me go to the other thing I promised I would do, which is to consider the Poissonian processes that you need to do at least half of the problems I gave you require the Poissonian approximation. Remember, it's the limit of these distributions that we can be studying when n is a very big number, p is a very small number, such that n plus p is a constant. That normally in Poissonian theory people call lambda, but it's some constant. Okay? So remember, p is very small, so q is approximately 1. Okay? Because p plus, so this is a binomial. Only that the probability of one of the things is very big, very close to 1, the other is very small. And you will see when these things apply. So we are in the case when n plus is a number much, much smaller than n. And n minus is a number of order n. Okay? So when you're studying processes that have very small likelihood, and you want to study what is the probability of getting 1, 2, 3, or 4 events of that small process. So what is the approximation? The approximation is very simple. Remember, what we are trying to approximate is this. P to the n plus, Q to the n minus n plus. This is the exact result. Okay, this is the binomial. I am going to approximate under these circumstances. And then there are two things that I want to do. I will leave certain things without touching. P to the n plus, I will leave it as it is. N plus factorial, I will leave it as it is. But I want to approximate two quantities. One is this, n factorial over n minus n plus factorial. And the other quantity I want to approximate is this, q, which is 1 minus p to the n minus n plus. So I just rewrote this because I am going to do approximations on the second and third term here. So let me show you what is the approximation. I am assuming this is n times n minus 1 times n minus 2 all the way to n minus n plus 1. Okay? That's exactly what that is. The factorial is all the product to 1, but since I have at the bottom all the other ones, I have these numbers. And you see, n plus is much smaller than n. So if this number is a billion, this is 999, blah, 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 and this is 999,900,000, and it stops very close to that, because n plus is a small number. So the idea then is that all these numbers are practically of order n. So we are going to approximate them simply by n. So this will be n multiplied to the, what do I have? To the n plus. Because how many do I have? 1, 2, 3, until n plus. So this I will approximate as n to the n plus. This is here. And this number, there is another approximation that you will agree that is quite precise. P is a lambda over n. Remember I said that n times p is the number lambda. So this is 1 minus lambda over n to the power n minus n plus. Where again, this number is almost n. This is 10 to the 22, and this is a much, much smaller number. And I hope you remember where you have seen 1 minus lambda to the n, to the lambda over n to the power n, when n is very big, this goes to the exponential of minus lambda. If you want, try it in Mathematica, write 1 minus 3 to to the 50 to the power 50, 1 minus 3 to over 51 to the power 51, and see all this sequence, and you will see that it becomes closer and closer and closer to e to the minus 3. If n is a very big number, this is an exact approximation. And you can check in many orders of magnitude, this will be very correct. So let me replace there. What do I get then? I get n to the power n plus factorial that I have here, e to the n plus and e to the minus lambda. That's all I get. At an n times p is what I call n plus. So this is lambda to the power n plus over n plus factorial divided e to the minus lambda. This is what's called the Poissonian approximation. So I approximate the binomial by this. The probability, what does it mean? What exactly reads there? The probability of n plus being 0, n plus equal to 0 is lambda to the 0 over 0 factorial, it's e to the minus lambda. The probability of n plus being 1 is lambda e to the minus lambda. The probability of n plus being 2 is lambda squared over 2 e to the minus lambda, and so on and so forth. Okay? I am approximating the actual binomial by these numbers. And you can convince yourselves that this is a perfectly defined distribution, because you always have to convince me, you do approximation, that if you sum over all values of n plus, you still get the number 1. And so if I sum e to the minus lambda over the sum of lambda to the power n plus over n plus factorial, and I sum when n plus goes from 0 to infinity, what do I get? This is the expansion of e to the lambda, right? Lambda to the something over something factorial, sum over something is the expansion of e to the lambda. So this is e to the lambda, times e to the minus lambda gives me 1. So this is indeed a correctly defined distribution. You can check, and I believe I have it in the computer. If not, I will show it next time. I'm sure if I open my computer, I can find it there. That this expression actually approximates quite well the binomial, particularly when n plus is a small enough number. For n plus equals 0, 1, 2, 3, 4, 5, it's a very good approximation. When n plus becomes very small, when n plus becomes very big, and this number starts to become smaller, well, by the way, let me see what this looks like. And I believe I have it in my computer, but I'll show it. If I plot these numbers, I will get something that goes like this, and then it decays. You can convince yourself that the maximum of this expression, well, you can take the derivative. E to the minus lambda, lambda to the n plus over n plus factorial. Well, the derivative is more difficult, but if you, for example, try to calculate the average of this distribution, you have a question?
Yeah, I was just wondering if you could possibly explain one more time how we got n to the n plus in our previous.
Well, because I had n minus 1, n minus 2, and I stopped at a number quite close to n. So all these numbers are very big. Imagine that n is 10 to the 22 and n plus is 50. So you have 10 to the 22, 10 to the 22 minus 1, 10 to the 22 minus 2. These are all numbers very close to 10 to the 22. And you have how many of them? 50. So that's where you got it. So, and I will try to open my computer now and show you, because the expression is like this. You can convince yourself that is easy to calculate. Where is the maximum of this expression? And where is the average of this expression? You because this is a distribution. So a fair question is, what is the value of n plus where this peaks? And it will be with n plus is of order lambda. And that's easy to show. That part is easy to show. I want to calculate the average value of n plus. Okay? Did I do it here? Yes. In other words, what I want, imagine the Poissonian, let me call it Poissonian of the number n, but I want to calculate the average value, the sum of m times the Poissonian of n. The Poissonian of 0 is e to the minus lambda. The Poissonian of 1 is lambda e to the minus lambda. The Poissonian of 2 is etc. etc. And I want to calculate this, to calculate the average value of n, to see what is the average. And so this is e to the minus lambda times the sum of n lambda to the n over n factorial, yes? So before I called it n plus, but it's the same, it's the variable n. And this goes from 0 to infinity. And I want to calculate that. Without the n, remember, we did this sum and we said it was e to the lambda, but now we have an n there. So we have to take care of that, and that is the same as saying e to the minus lambda times the sum of lambda to the n over n minus 1 factorial. Okay, because I have n factorial, but I have an n. And this sum doesn't start from 0 anymore, because when n is 0, this term doesn't come, so this goes from 1 to infinity. And then it's pretty obvious what I have to do. Take one lambda outside, you get lambda e to the minus lambda times the sum of lambda to the n minus 1 over n minus 1 factorial from 1 to infinity. Call n minus 1, call it n prime, and you get from 0 to infinity now lambda of n prime over n prime factorial. This is e to the lambda, which cancels that one, and you get just lambda. So the Poissonian distribution will have a maximum at around the parameter lambda, and then it decays. Okay, so if lambda is 5, the Poissonian of 0 will be a number, of 1 will be a little bigger, 2 a little bigger, 3 a little bigger, 4 a little, 5 is the maximum, and then it starts decaying. And it decays quite fast because the factorials decay very fast. Remember, factorials decay really grow very much. So that is the factorial, and okay. So let me just give you a couple of examples and how you use them, so you will understand. What is ringing if I took the ringer out? I don't know. Okay, let's start. Oops. Let me do a few examples. So not examples, just for you to build. Here I took one example. Yeah, I have a couple of examples to tell you how you work with that. One, I will pick one of the problems I assigned so that you get a feeling of how to work. But look at even a simpler example. Imagine that you have a sample of 10 to the 20 atoms of something. A very big number, 2 grams of some uranium or something that decay. And you measure that you count 3 decays per day. Okay, this is the average. Okay? So what is the probability of one atom to decay? If on average you have 3 decays per day, is 3 over 10 to the 20. Right? So the little p, the probability that one given atom decays in a day is this. Because you have 10 to the 20, on average you get 3 decays per day. And of course your n is the very big number, 10 to the 20. So your lambda is the number 3. It's this times this. Okay, so I have a process in which, and I am asking what is the probability that in one day I have no decays? Well, the probability will be p of 0. which is e to the minus lambda, lambda to the 0 over 0 factorial, or e to the minus lambda, e to the minus 3, which is 0.05 approximately. So the probability that in one given day I have no decays will be around 5%. Yes?
Does this work as a good approximation even when lambda is like 20, or is it only?
Yes. No. This will work for, yeah. The only, you will see, this will not be very good when you are trying to apply to numbers much bigger than lambda, where these numbers are really very small. Now the probability will be 10 to the minus 7, and the Poisson approximation will give you 1.5, that will give you a 50% error perhaps, but only in the small numbers. If you do instead of this, the probability of getting 0, what will it be? Just do it. If we don't want to do the Poisson approximation, is the probability if each atom decays with probability 3 times 10 to the minus 20, the probability that the given atom does not decay is 1 minus 3 times 10 to the minus 20, right? And the probability that no atom decays is this number raised to the power 10 to the 20. You agree? This is the exact thing. This is the approximation we did. This is the exact thing. Okay, and well, this is 1 minus 3 divided 10 to the 20 to the 10 to the 20 is e to the minus 3, I am sure with 17 digits. I'm sure that you can do that and check in the computer. If you could calculate that, you will get e to the minus 3, which is exactly the same. So let me get the next one. What is the probability of getting one decay? Poisson tells me that this is e to the minus lambda, lambda to the 1 over 1 factorial. Or in other words, 3 e to the minus 3. Okay? Are we right? Yeah, 3 to the, so this is 0.15. Okay, so there are 15% chances that I will get just one decay. But let's try to calculate it exactly to see if this is a good approximation. What would it be, the probability that only one decays? That one particle decays with probability 3 times 10 to the minus 20, that all the others do not decay with probability 1 minus 3 times 10 to the minus 20 raised to the power 10 to the 20 minus 1, because 1 has to decay and all the others must not decay to get 1. And I have to multiply this by the combinatorial, right? Which is all the ways of choosing one atom from 10 to the 20, which is, as you know, 10 to the 20. How many ways do I have to choose one atom out of 10 to the 20? 10 to the 20, because I can choose any one of them. If you calculate all these things, what do you get? The 10 to the 20 and the 10 to the minus 20 cancels, and you get 3 times 1 minus 3 over 10 to the 20 times 10 to the 20 minus 1. This will be again e to the minus 3. So you get 3 times e to the minus 3. So you see that indeed, if I calculated the thing exactly, I would get this very much. And you can try. I mean, one of the problems I gave you, I said, calculate this. I forget what is it that I asked you. I said, calculate this doing the exact combinatorial, and then do the same using the Poissonian, and compare the table, and you will see, I believe the lambda is around 4, and you will see that for 0, 1, 2, 3, 4, 5, 6, 7, practically with 5 or 6 digits you get it right. Only in the last ones that have very small probability, you might get a 30% off. When one of them should be 10 to the minus 9, you will get 2 times 10 to the minus 9. But only in the very, very fast tail, last tail of the distribution. But for the main part of the distribution, when the probability is big, you get a very good approximation. So this was one example, but let me show you in 2 cases Well, one is the problem. I gave you an interesting problem because it's a real life problem. So in some sense I am telling you the solution, which was the problem of the airlines. So, you know, the story is that the airlines never sell the number of tickets, the number of seats they have in the plane, because since there is a relatively big chance, around 1 in 12, that the passenger doesn't show, if they do that, they will always, on average, have 1 in 12 seats empty. And that is losing money. So in order to avoid that, they oversell. And that's why, from time to time, they oversell too much, and chances are chances. You arrive to the airport, and it turns out that there are more passengers than seats, and they start losing money because they have to offer you something, and so on. So I said, imagine that if the chances, 1 in 12 is the chance of a passenger not showing up, which is apparently the statistics in the industry. I assume each airline has their own. Let's say you have a plane of, I don't know the numbers I used there, but I am making it up. Imagine that you have a plane of 50 seats, and if you sell exactly 50 seats, on average, 50 over 12, which is 4 approximately seats, will go empty. Some flight might not, some flight might 7 seats go empty, but you want to compensate for that by overselling. So the question is, if you say sell 55 seats, what are the chances of that every passenger that shows up finding a seat? Or let's say 55, yeah. And the question is, what are the chances that when the passengers arrive to the airport, they show up? Well, this problem can be cast as very simple. This is the probability that the number of passengers showing up is 0, 1, or 2, or up to 50, but not 51 or 52. Or the probability of to having a number of show-ups which is smaller than that. If I calculate, let me do it the other way around, which is easier. Let me calculate the probability of a no-show. A no-show will have a probability of 50 over 12, right? Because if there are 50 seats there and 12, the probability of a no-show will be 50 over 12. So I want to calculate what is the probability that the number of no-shows doesn't exceed, is smaller than 5. Because if the number is smaller than 5, I am fine. But if the number is smaller than 5, I am in trouble, because that means that there will be 51 or more passengers.
What's 50 over 12? The probability of what?
The probability of a passenger not showing up at the airport.
I thought that was 1 over 12.
No, 1 over 12 is 1 passenger, but in my plane, which has 50 seats, it's 50 over 12, okay? 1 over 12 is 1 passenger. But in my flight, actually, which has 50 seats, this is the average number. This is the average number of seats that will go. So this will be my lambda. So I want to calculate the probability that the number of seats of no-shows is not bigger than 5, because that will bring me trouble, because I sold 55 tickets. If the number of no-shows is smaller than 5, somebody will not get a seat. So, and that the number is smaller than 5 is 1 minus B0, the probability of 0 no-shows, which means the 55 people that got tickets showing up there, minus B of 1, minus B of 2, minus B of 3, minus B of 4. That's it. If that is the probability that the number of no-shows is 5 or bigger, because I discounted all these. If the number of no-shows is 5 or bigger, I am fine. If the number of no-shows is smaller than that, so you calculate and you will get whatever, 20%. So this airline is doing something that in 20% of the cases might lead to trouble. 20%. And so if they say no, 20% is not acceptable, that in 20% of our flights we have trouble. Well, then what they will have to do is sell less tickets, say sell 53 tickets, so they stop here. So then this number will be 10% or whatever. So then we say, well, okay, I am willing to risk that in 10% of the cases, I will have to compensate some passenger, but 10% is okay. Because the money I save by selling these extra tickets, the other 90% of the time is okay. So the airline has to sell, so probably you will have to try replacing this one and see where you stop if you want less than 10%. So that's one case of application, and this is what we said, e to the minus lambda, this will be lambda e to the minus lambda, this will be lambda squared over 2 e to the minus lambda, etc. So you have to summon those and calculate. So that's one example. Let me show you one example where it's more interesting. This might be very interesting if you are running an airline, which someday I hope you will. And we have 2 or 3 who was with me in the study. You were in the study of the airlines, right? Okay, so someday you will run a consortium of airlines and you will have to face these problems. So, but let me consider another case, which is of interest. Imagine a very famous thing, you know, there are theories that claim that that the proton is not a stable particle and can decay with a very small probability. That's why we don't see protons decaying every day. We believe it does not, because it's the particle of all the elementary particles, the one with the smallest energy. So neutrons decay and form a proton and an electron every 20 minutes and so on. But the proton, according to certain theories, does decay. So you do an experiment, and you see it's very difficult when you want to do an experiment to see if something doesn't happen, okay? You observe and nothing happens, and what do you know now? Well, you can say, well, if I keep running, perhaps it will happen. So what you do is the following. So you do an experiment, and you say, well, I will observe for 5 years in a row and see what happens. You observe for 5 years, and what happened? That no proton decays. Okay, so you will say, well, I have reasons to believe that protons do not decay. But with what confidence do you say that statement? Because somebody will say, well, 5 years, why don't you wait 20? Why don't you wait 50? How do you know what confidence you are giving me? And so the idea is simple. You say, well, if 0 events happen in 5 years, what I can say is the following, that the probability of this event is lambda e to the minus lambda over, no, it's 0, okay? It's lambda to the 0 e to the minus lambda over 0 factorial. So this is e to the minus lambda. Okay? So this is the probability that an event that has a certain probability lambda that you don't know what it is, during a certain period you have 0 events. That's the probability. So if you say, I want to affirm with 90% confidence what I'm going to say, you say this has to be 0.1 or smaller. Then, with 90% confidence, I can say that. So that is putting a limit in lambda, because the lambda is 2.3. If you solve this equation for lambda, you get 2.3. So what you can say is the following, that lambda in this event is 2.3. But what is lambda? Lambda is the number of events per unit time times your time, right? So, and this is 2.3. So that means that since t is 5 years, 2.3 over 5 years is 0.4 events per year. So you can say, with 90% confidence, I can say that this process has a rate which is smaller than 0.4, it's no bigger than 0.4 events per year. So you can say with 90% confidence, the rate at which protons decay in this particular sample is at the rate of 0.4 events per year, or less, because that's what I observed. Let's say you are not happy with 90%, or the editor of the paper where you're submitting the article says, no, we don't want statements that are 90%, I want 99%. Well, if you want 99%, you want this to be 0.01. You want your event to have probability of 0.01 or smaller. If you put here 0.01, the lambda that you have to solve is twice as big, it's 4.6. So then you will say, with a probability of 99%, the rate of this event is smaller than 0.9 events per year. So I can assure with probability 99%, with confidence 99%, there are less than 0.9 decays of a proton per year. If I want to say with more certainty, well, then it's only 90% confidence. So you see, that's a simple use, and it takes us a little bit away from the content of this course, because this is a statistics use. I mean, but in courses in statistics, you use that to estimate the probability, with what confidence you can say from observing that something doesn't happen, that the rate is smaller than something. I gave you another example there, a problem in which it says that you are observing photons or neutrinos arriving, and you have a background. You know that you can expect to have this many neutrinos per day. Say 1 neutrino per day comes from the background, because you measure during time, and there are phenomena, alterations, and you have a background. But then you run your experiment and you discover that after 3 or 4 years of looking, during 1 hour you get 3 or 4 neutrinos. And well, you want to know, is this a signal that there was some event, some real event, a supernova or something, or is it just a regular fluctuation? And so you have to calculate what is knowing that the probability of a random event is 1 per day, what are the probability of getting 3 in an hour? And you calculate, and you will find out that if the rate is 1 per day, if you observe long enough, you have a reasonable probability of having a fluctuation of 3 per hour. In 1 given hour, you will find the probability is very small, right? Because if you have 1 event per day, it's 1/24 per hour. But you are not doing 1 experiment. You are looking for 5 years, so you are doing this multiplying for an n which is very big, because in 5 years there are many hours. So you will discover that the probability of getting 3 events in an hour is like 25% by chance. Well, then don't tell me that this is a supernova if there is a 25% chance that this can happen by accident. Nobody will believe you. So you can do estimates using the Poissonian processes for many things in real life. So I will leave those to you, for you to start playing around, and I will switch directions now and go to a little bit of starting building the theory of ensembles. So I don't have too much time, but at least in the little bit of time that I have, I will start to discuss what is the connection of this probability analysis that we have with the concept of thermodynamics that you heard about, temperature, entropy, etc. And so the idea and the way this starts is saying the following, that when you have a phenomenon and you have many micro configurations that can correspond to a certain macro state, remember, like in our case, that we said the state where there are an excess of 7 spins, is G of whatever, is that is the number of micro configurations consistent with my external state. So when you have a system, normally, if the system is isolated, now I'm talking about the physical system, one thing you know for sure, if the system is isolated, the energy is a constant. The energy cannot change in systems that are isolated because energy is conserved. So when you are looking at your state, if it is isolated, the energy is a constant. So if I ask you, let's say, remember I showed you that the energy was minus 2 msv, the energy of a given state, right? Where S was the number of spins up minus the number of spins down over 2. So it depends on the excess spin. Okay? So let's say that I tell you that this is the energy, and I ask you, what can you tell me about the system? You say, well, it has to be in a state where the number of spin up minus number of spin down over 2 is precisely this S. So let's say that S happens to be 3. So that means that you are saying that n plus minus n minus over 2 is 3. Or let me see, what did I pick here? No, I picked 3 up and 2 down. So S equals to 1. Okay? And n equals to 5. So if you say that the energy is that, you know that the system has to be in a state in which there are 3 spins up and 2 spins down. Cannot be in any other. But there are many, because you can have this one, or you can have this one, etc., etc. And we calculated that there are 10 possibilities here, right? So what we say is the following, that then I build in my mind many copies of the system, each one in one of these possible states. So I will have 10 copies of my system. Each one is one possible state. The physical statement that Boltzmann came up with is saying that the system is as likely to be in any of these states. We don't have any reason to assume that it will be this one or this one or this one. Any state that is compatible with external constraints, in this case that S has to be the number 1, is a possible state of the system. So he said, if you want, or Gibbs actually came with the idea, if you want to study the statistical properties of your system, just do the following. The system, as time goes on, might go from this configuration to this one. We don't know how it's reacting. But it's as likely to be here than here than here. So if you measure a little later, might be here, but it cannot be in this state. Because if it were in this state, the system gained energy from somewhere, and that cannot happen. So, but since it's as likely to be in any of these states as in any other, you take your G of 5, 1, which in this case is the number 10, okay? G of NS is the number 10, because remember this is the combinatorial 5, 3. Remember 5, 3 is 5 times 4 over 2, so it's 10. And you say, what is the probability of this state, of this state, or this state? They are all equal. So each one will have probability 1/10. So I imagine that I have many copies of my system, but such that each one appears with probability 1/10. All are with equal probability. So if I need to calculate whatever property I need from my system, and I will give you examples of what is it that I might want to calculate, well, instead of calculating in a real system that you cannot know what is happening because you cannot look inside, you calculate average over the members of your ensemble. So this is the simplest ensemble in which you state any state whose energy is different from the energy of a state has probability 0, cannot be there. And any state that is compatible with the external constraints, in this case the energy, has the same probability that any other. So the probability will be 1 over G, okay, because there are G of them. So this is what is called the micro-canonical ensemble. It's the mental process of replacing my real system by as many copies of my system as different states I have, that they are all in different states. And anything I need to calculate, statistically, I calculate over these 10 copies. Only that, of course, in our systems, there will not be 10, it will be very big numbers. But you see, the main assumption here is that systems have constraints, and you cannot measure, the system can never be in a state that is not consistent with those constraints. For example, conservation of energy is one of them. Conservation of the number of particles. You cannot have, if you say that the system is closed and nothing can happen, always you have to have 5 here. So you say, well, my system has n equals to a certain n0 and an energy equals to a certain u0. We'll address later with what precision I can know this, because when we have 10 to the 20 spins, it's not that simple to say the exact energy. You see, flipping one spin is very small, so we'll address that problem later. But in principle, imagine. So we say any possible microstate that has this n, this, that has at n equals to n0 and u equals to u0 is a possible state, and you have to take it with equal possibility. So if they have g of them, each one has probability 1 over g, period. Any state that doesn't respect any of these two things has probability 0, and I don't count it in my ensemble, because with probability 0 I don't have to include it. And then any mathematical calculation I need to do, any physical calculation, what is the temperature, the pressure, I do it averaging over these numbers. So, for example, in the example I picked here, or let me see if I did pick it. Yeah, I said I should have printed it because it would have been easier, but well, when you are lazy. I wrote the 10 states as I was describing, of 3 spins up and 2 spins down. So I will do a few, and you will help me if I miss one. 2, 2, 2, 2, and you will see there is a point of that. 2, 2, 2, 2 up, and well, I had a 10. I don't want to do a 10, but okay. There are 10 of these. You can convince yourself that there are 10 of these. So I say my ensemble is 10 copies of this. And so, and each one will appear with the same probability. The system is as likely to be in one state or the other. So what does it mean? Let's say that what I am trying to calculate, for you worked for a while in the Ising model. In the Ising model is a model in which you say that when 2 neighboring spins point in different ways, it costs you energy to do that, because spins like to point the same way. This was not our case, because in our case we were assuming that each spin is independent of the neighbor. But let's say in this case, 2 spins like to be like that. So if you want to count the energy of each of these states, well, in this one there is only one place where you pay a price, okay, between here and here. But in this one you have 1, 2, 3 places where you pay a price. And in this one you have 1, 2, and so on. And in each of the 10 states, you will calculate that. So if I ask you, what is the energy that you are paying to have a system of 5 spins? Well, you will have to average those numbers and get a number. How do you average? You sum all of them and you divide by 10. Because the underlying assumption is that the system is as likely to be here, or here, or here, or here, or here. Okay, so that's the physical idea behind statistical ensembles, and this is called the micro-canonical ensemble. Why is it called like that? Because very soon, next class, I will present another type of ensemble called the canonical ensemble, in which we liberate the system of the constraint of having the same energy, because when you have an object in a thermal bath, the energy can fluctuate. So that's a different description, because I have to include cases in which my system has more energy or less energy than the others. But here it does not. So I have presented this, and I said, the mathematics of this is very simple. My ensemble has as many elements as G, and the probability of every one of them is 1 over G. What can go wrong with them? Well, in most systems this is true, but there are certain cases in which we know that there are systems that do not go through all their possible states. For example, the typical example is one that's mentioned in the book by Kittel. If you have a quartz, which is normally a random disordered material, at very low temperatures, the quartz becomes like a crystalline state, and it's fixed in state. So not all the possible states are possible. So, and we know that you can wait forever with a piece of amorphous quartz, and it's not going to become ordered. You would have to heat it very much and do many things that you're not doing. So if you're looking at amorphous quartz, although you are counting all the states, you have to say, I have to count all the states by eliminate the ones that I know the system cannot acquire. So it requires a little bit of practice to say what is not reachable. But the statement is, of all the reachable states of my system, the system is as likely to be in any of them, and all of them with the same probability. So that's the philosophy here. Why do I tell you all this? Because now we will address the problem, next time, not today, the problem which is crucial in order to define our concepts of entropy and temperature, which is, let's say I have a system that has a certain energy. And so I know that it can be, a system N1, and is in a state with energy S1. So I know that there are G N1 S1 possible states, and it can be in any of them with the same probability. I have another system that has N2 states and has energy S2. And they are both isolated, so this has G of N2 S2. Okay? So the question is, let's say I bring them together and I put them in such a way that what the systems can do is exchange energy. So what does it mean? The total energy has to remain constant because I put them in contact, but they are isolated from the rest of the world. Since the energy, remember, of one of them was minus 2m S1b, and the energy of the other is minus 2m S2b, the total energy will be minus 2m S1 plus S2. So S1 plus S2 has to remain fixed because the systems cannot interact with the outside world. But there is the possibility that S1 and S2 can change. So one spin here can flip, but another spin in the other side flips in the other direction. Okay, so instead of having 10 pointing up and 6 pointing up, I can have 11 here and 5 here, or 12 and 4. As long as the sum is 16, this verifies conservation of energy. But in which state will it be? What will happen? So, because remember, if a spin flips, there is another flips here, there is energy going from here to here. In which direction will the energy flip? What will be the state in which the system will be? Because you see, in principle, when I put them together, if this can be in 20 states and this can be in 30, they can be in 600 states, 20 times 30. Okay, but if now they can be in many states, so I will have G of N1 S1 times G of N2 S minus S1, but S1 can take any value. You see, this can increase by 1 as long as this decreases by 1. So there are many more states. So my question is, in which one will the system settle of all these that are now possible, compatible with conservation of energy? This is the problem that Boltzmann thought and tried to come with a solution of what will happen when two systems can exchange energy. They are isolated, but they can exchange energy by themselves. What are they going to do? What value will S1 acquire of all these possible in the sum? Or will it be a little bit in each of them? Or what is it happening? That's what we are going to analyze next time. And that leads directly to the idea of entropy and temperature. So that's what's in store for next time. Good. So I'm stopping here. You're stopping here.